right, so it defines vectors up here. It talks a little bit about it. Many physical quantities, such as speed, can be completely described by a single real number called a scalar. Scalar is something that you would have used in geometry to like enlarge and shrink, okay? This number indicates the magnitude or the size of the quantity. A vector is a quantity that has both magnitude and direction. The velocity of a football is a vector that describes both the speed and the direction of the football. All right, also the players. Often football is used for vectors. When you're talking about vectors, it's twofold. You have two parts that play into this. The magnitude or the size of it, as well as the direction of it, okay? And so magnitude is going to be what you're going to use like a distance formula for. And then direction is going to be angular direction, okay? So let's talk about when a vector would possibly need to be used. Let's look at this first example. State whether each quantity describes a vector or a scalar. Could you describe it with just one thing, or would you need two things to describe it? The first thing is a boat traveling at 15 miles an hour. This quantity has a magnitude of 15 miles an hour. Did they talk about direction? No. This is scalar, right? All they told us was how fast it was traveling. One thing affects this boat. Now, legitimately, it's traveling a direction, but this particular problem did not have anything to do with direction. It just told us about how quickly it was traveling. B, a hiker walking 25 paces due west. Is this a vector or a scalar? Vector. They told us the pace at which this person was traveling and the direction that they were traveling. This is a vector. All right, let's look at the third one. A person's weight on the bathroom scale. Scalar. All right, okay, so this is kind of a tricky one. All right, let's think about weight. All right, yeah, so when they talk about weight, there's a gravitational push on it, which is down, okay? And this comes into effect when you start getting into like propulsion. All right, with propulsion, there's things that affect it. One thing that it affects it is its weight. And so they will often say with propulsion, especially when you get into like physics, the weight on Earth. Why? Because there's actually a gravitational force that's there. So this is actually considered a vector quantity. Person's mass plus the downward pull due to gravity. There's two things that are affecting this. There's two things that are affecting weight. All right? Because if I were to take that same person and put that person on a different planet, you would see that weight would change, but their mass did not. Does that make sense? So there's two things that are affecting weight. It is the mass of the object and the gravitational pull on whatever is pulling on the object itself. Okay? A car traveling 60 miles an hour, 15 degrees east of south. Yeah, that's vector. A parachute falling straight down at 12.5 miles per hour. Yeah, they told you down. A child pulling a sled with a force of 40 newtons. Scalar. They didn't tell you anything about direction there. A vector can be represented geometrically by a directed line segment, an arrow diagram that shows both magnitude and direction. Consider the directed line segment with an initial point. All right, so you'll notice it is a ray, that term from geometry. We have an initial point, also known as the tail, and a terminal point, B, also known as the head or the tip. So you have a tail and a head, all right? You'll notice the arrow that tells you which direction we are moving. It is denoted, it looks similar actually to a notation for a ray. However, you'll notice that it has just one of the arrow tips on it, where a ray would actually have the full arrow, if you remember the notation from geometry, okay, for a ray. Order matters. So A is the initial point, B is the terminal point, okay? The reason order matters when you write this is because you would have a different vector if you went from B to A, all right? If this was a line segment, it wouldn't matter. Line segments don't have direction, but vectors matter, just like rays matter. Your initial point and your terminal point need to be in the correct order. You'll also notice that because we had this little a right here, they could use the lowercase a with the same notation, or they did a bold a. I will say for the most part in this book, you're going to see this AB. All right, you're going to see your initial and terminal point listed. But all three of those are acceptable notation for these. If a vector has an initial point at the origin, it is called standard position. By origin, I mean on a coordinate plane 0, 0. All right, so this is considered standard position because it starts at the origin. All right, the direction of the vector is the directed angle between the vector and the horizontal line. All right, so the direction of the vector is the angle that is created between the horizontal and the vector itself. Now that does not matter if it's in the original position. That's still going to be, if you were to slide it down to the origin between the x-axis and that guy, or if you were to draw a horizontal right here, it would still be the angle between. All right, so the direction is the angle between the vector and the horizontal line. Could be used to represent the positive x-axis, which is what you see here. So in this case, the direction of this is 35 degrees. The direction of this is 35 degrees. So in standard position, it's from this horizontal, all right? When the length of the line segment represents and is proportional to the magnitude of the vector. If the scale of the arrow diagram for A is 1 centimeter equals 5 feet, then the magnitude of A denoted, and it looks like a little absolute value because length is always positive, 2.6 times 5 or 13 feet per second, all right? So when we talk about magnitude, we are talking about somewhat twofold, all right? So they told us right here 1 centimeter is 5 feet per second, 5 feet per second. And so if we were to measure this 2.6, so if this were 2.6 centimeters, you have to basically convert it. 2.6 times 5, 13 feet per second. So think of it as a legend on a map, all right? Does that make sense? A legend on a map. It says 1 inch is equal to 100 miles, all right? And you would say, oh, this is 3 inches, so it's 300 miles apart, okay? It's almost like a legend on a map is what they're telling you there with that. Let's talk about quadrant bearing. The direction of a vector can also be given as a bearing, a quadrant bearing, or phi. So phi is the Greek letter right there. Do not ask me to draw it often. There we go. I mean, it's going to look a little different when I draw it, right? But there he is. Directional measurement between 0 and 90 degrees, east or west of the north-south line, all right? The quadrant bearing of a vector V shown is 35 degrees east of south or southeast, okay? What does that mean, all right? So, this is how this guy's written right here. Southeast, 35 degrees, okay? What they mean is east of south. So first of all, do we all know our north, south, east, west? So this is north, south, east, west. So what do they mean by that? South, 35 degrees east. They mean east of south, 35 degrees. All right, so that means between here and here is 35 degrees. All right, somewhat. So how then do they know that this is 145 degrees? Because this is 180. A line is 180. The reason I'm telling you this is because there are going to be times when you need to use the 145. And they're going to say 35 degrees southeast. And they're going to give you this guy, and you subtract from 180 to get that guy. Everybody understand?
Is it always coming off of your leg?
So quadrant bearing, they're going to write it this way, and they're going to say southeast 35 degrees, which means southeast, east of south. That means this little angle right here between the south and your vector east of the south is 35 degrees. So 35 degrees they have given us right here, southeast. Okay? Now, there's a difference between that and true bearing. True bearing is a directional measurement where the angle is measured clockwise from north, okay? True bearings are always given using 3 digits. So a direction that measures 25 degrees clockwise from north would be written as 025 degrees, okay? always from north, clockwise. All right, so if they gave me this 0 to 5, then it would be about right here. 25 degrees clockwise from north, okay? So there are different ways they can give this to you, all right? They can give it to you in standard position. Standard position, think of it the same way you would for a unit circle. Standard position starts at the origin and it goes counterclockwise from the x-axis, standard position, all right? Quadrant bearing. Quadrant is going to give you your north, south, east, west. So they're going to say east of north, northeast, west of north, northwest, and they're going to give you degrees. True bearing is always going to start north, straight up, and go clockwise. And it's going to be in 3 digits, okay? All right, so let's look at this.
Boo.
It says use a ruler and a protractor to draw an arrow diagram for each quantity described and include scale in each diagram. A equals 20 feet per second at a bearing of 030. So first of all, this right here tells us that they gave it to us how? True bearing, all right? Those 3 digits told us it was true bearing, all right? True bearing. 20 feet per second. Basically, if they want, this is 10 feet for every 1 inch, this guy should have been 2 inches long, all right? So that's all we're looking for, is that you know the conversion, all right? But most of the time, your word problems are going to tell you 20 feet per second. They're going to say that. You're not going to have to measure and calculate, all right? What I do want you to be able to do is if it says this bearing right here, you know to start north and to go clockwise 30 degrees, okay? How does this help you? Well, if I know that's 30, what is this guy? 60. How do I know that's 60? Because it's in a quadrant and each quadrant's 90 degrees, okay? This is going to help you when you start doing SOHCAHTOA, because there are times when you're going to need to use the 60 and create this little right triangle here. And there are times when you possibly may use the 30 and create that right triangle. But you need to know how to get both of those based on what they gave you. All right? It says 75 pounds of force at 140 degrees to the horizontal. To the horizontal indicates standard position. To the horizontal indicates standard position, which means just like we would have done with a unit circle, we're going to start at X and we're going to go 140 degrees counterclockwise. All right. The 75 pounds of force is telling you the length. Okay. 75 pounds of force is telling you the length. The 140 degrees to horizontal is telling you how you got that angle and that movement. Okay. Let's look at the next one.
So, what do we find?
All right, the last one, 30 miles per hour at a bearing of south 60 degrees west, okay? So the 30 miles per hour, that is just telling you how long it is. Think of it as how long you're traveling. 30 miles an hour, okay? That's giving you a magnitude, all right? Your direction is 60 degrees southwest. So I'm gonna go south, all right? South, and west of south is this way. West of south is this way, and it's 60 degrees west of south. West of south. All right? Does everybody understand that one? Southwest, we're going to go southwest. All right? 60 degrees south, west of south. West of south is how you're going to think of that. Parallel vectors have the same or opposite direction, but not necessarily the same magnitude. Think about parallel lines. Obviously, lines are infinite both directions, but it doesn't matter which direction you're going on the vector if it's parallel. Same or opposite direction, but not necessarily the same magnitude, okay? So they can be going from start to finish, but as long as the direction itself is the same, it doesn't matter if it's opposite or the same, as long as it is absolute value the same. In the figure A, and this is your parallel symbol, which is the exact symbol you would have used in geometry. A is parallel to B, which is parallel to C, which is parallel to E, which is parallel to F. All of these are parallel lines. This guy visually makes you not think they are, but they are. Equivalent vectors. They have the same magnitude and direction. All right? The same magnitude and the same direction to be equivalent. That example they give you is A and C. They are parallel. Their direction is the same. The arrows are pointing the same direction. And the magnitude is the same. The length is the same. A is not equivalent to B because the magnitude is different. A is not equivalent to D because they do not have the same direction, even though they have the same length. Both has to be the same. Magnitude and direction has to be the same to be considered equivalent. Opposite vectors have the same magnitude but opposite direction. Opposite is written with a negative sign in front of it, which means opposite in every world, right? So here, A is opposite to E. And you can see that being the case, opposite direction, all right? While the angle of the direction is the same, they're parallel. They're going different directions, opposite directions. So two or more vectors added. Their sum is a single vector called the resultant. The resultant vector has the same effect as applying one vector after another. Think about it this way. If I were to walk towards Bobby and then walk towards Alyssa, if I added those movements together, it would be as if I walked straight to Alyssa. Same result, okay? Does that make sense? And so there are different ways to combine these vectors to get what you're trying to get, pretty much, to get to where you're going, all right? They can be found using either the triangle or the parallelogram method, all right? So triangle method, tip to tail. So you have these two vectors here. If I were to translate this so that they're touching, the tip of one is touching the tail of the other. Remember tip, tail. The tip is where you start. The tail is where you, one start, one end. So you have to have a start and an end together. And it doesn't matter which one. The resultant vector is from A to B, like this. The other way you can do it is creating a parallelogram. All right, you can basically slide it past here, and then you create this parallelogram. All right. And so they've created this parallelogram here. All right, and so we're going to actually use this in calculating these guys going forward. So two or more vectors. All right, two or more vectors. This is how you're going to see all of your word problems, pretty much. They're going to say, this is going on, and then this happened, or then they did this. You have the example they give you here is you're walking one direction, then you change direction, all right? And so you basically have two straight lines that are happening here, two vectors. You have an airplane or a boat, right? And they have either the current going against them or they have the air resistance going against them. They have winds blowing in a specific direction at a certain speed. And so you basically can create two different ways to do this. You can put them one after another, so it doesn't matter where they fall on the coordinate plane. You can just shove them together, because as long as the angle and the magnitude doesn't change, then you haven't really changed anything. You just put them together so you can visually see it. Tail to tip, right? So this is where you have this one connected to that one. Or you can slide it past it. You can create this parallelogram, which can often help you as well when you're doing these. Because if you remember when we did, compare it to like if you had your point of view type problems like we did in the prior chapters, like in chapter 4, where it was angle of elevation, angle of depression, right? Remember how you could rectangle those And you could say, okay, if my angle of elevation to the top of the mountain is this, then the angle of depression from the mountain down is that. You created basically a parallelogram, right? And then you said I could use either or. And that's kind of what you're going to think about if you were to do like a parallelogram type situation. All right? Look at this example they give us. In an orienteering competition, Tia walks north 50 degrees east, so northeast 50 degrees for 120 feet, then walks 80 feet due east. How far and what quadrant bearing is Tia from her starting position? And so you can do this two different ways. And basically, they're going to tell you in these situations to get a ruler out, to do 1 centimeter per whatever, and that's not really what we're going to do because that's not practical. But what I will say is you do have to visually be able to figure out what's going on. And so if she is walking north 50 degrees east, you do need to know what that means on this coordinate plane if you're going to use it. We're going to start north and we're going to go down 50 degrees, right, this way. And so this right here is going to be my 50 degrees, right? And then my 120 feet, that tells me how far she's walked. Obviously not drawing it to scale, but all right, so my vector is going to be here. My magnitude of my vector is going to be 120 feet, okay? Now, technically at that point, she walked 80 feet due east. So if I did tail to tip, it's just as though she was walking. I would stop right where she stopped, and then I would take a right or left if she's going due east. Due east, right or left? Which way did she go? Right, okay. So she is then going to start here, and she's going to go due east, right? Straight that way. And she's going to do that for 80 feet. And what they really want to know is how far and at what bearing is she from her starting position? Okay, that's what they want to know. So basically what they're asking here is, I want to know from her starting position all the way to here, right? I want to know what this is. And I also want to know the bearing. I want to know the degrees, okay? And so there's a couple different ways to do this. And I'm going to talk about both ways right now, because the way that they do it in the next example is they do it using law of sines and law of cosines, which is perfectly fine. We have a triangle that we can use that with. We have that 50 degrees. We have the complements of that 50 degrees that we can do something with. I also want to keep in mind that you can create perfect right triangles here if you want to figure that out as well. And so you can create right triangles. So if I were to take this, and I'll do it right here. You have a right triangle here where you have the hypotenuse of 120 feet, and you actually know this guy because it's the complement of 50, right? We know that's 40. And so we know that we can do some calculations with a right triangle there. Does that make sense? And we could potentially figure out this guy. And then if I were to do the same thing with this purple one here and do some type of a right triangle here, I can figure out this one. Does everybody see? And then if I want to calculate the hypotenuse, I can do that. And so you have some options here to try to figure out what am I doing? How am I doing this? And you have all of your options kind of in your back pocket from right angle trigonometry. All right? Does that make sense? And so what they want to make sure you understand when you do these is you've created either a triangle that you're going to use like this, which is what the next one does, where you do some sort of law of sines, law of cosines, because it is not a perfect right triangle, or you are considering the sum of the two right triangles that are kind of created by her movements, okay? And so those are kind of the methods you're going to see used in these word problems, all right? Those are the methods you're going to see. You're going to see creating just a triangle of any sort, using the tip to tail, and then using maybe law of sines, law of cosines, because you have an angle and a side, but you don't have the other angle and you need to figure out what it is. Or you have two right triangles that you are doing the sum of, right? The sum of, which is probably what you did in physics, like an x plus an amount and a y plus an amount or whatever. And then using SOHCAHTOA and backing into it that way, all right? You do have to keep in mind you are constantly going back and forth between complements, okay? They gave me 50. I may very well use 40 because that's the complement of 50. At the end, I want the true bearing there, right? And so at the end, I'm going to have to go back and say how far away from true north am I, okay? Because you may actually end up calculating some other angle, right? And then all of a sudden you have to back into your answer because you're not quite done yet. Does that make sense? So you have to constantly know what angle you solved for and what angle you need, or else you will give potentially the wrong angle as your answer. All right? And so my goal with these is that first of all, the hardest part's the setup, and then you're going to start using something you've already used to solve. All right? And it will be about vectors. If a vector is multiplied by a real number, the scalar multiple has a magnitude of k times v. Its direction is determined by the sign of k. So think about the term scalar way back from geometry. All right, when you did scalars, you literally just multiplied by the number, and that's pretty much what it's telling you here. You have a vector. You have a scalar of the vector. You are going to multiply the magnitude by the scalar, and it may change direction based on what you did. And so you just need to keep that in mind if you have a problem, real world situation where you have to multiply by some type of vector, okay? Where you can just multiply the magnitude by that. If they double their speed, you can double it. It's just a scalar multiplication there, just like it was way back in geometry, okay? This says, an airplane is flying with an airspeed of 310 knots on a heading of 050 degrees. If a 78 knot wind is blowing from a true heading of 125 degrees, determine the speed and direction of the plane relative to the ground, okay? So we have to consider two things here, the airplane and the wind, all right? And so you have to, one, be able to draw it, just to sketch it out. Not perfectly, but you do want to be able to figure out what exactly they're talking about when I have this. And so you do want to start in a coordinate plane type situation. So you want to start with your X and Y axis. All right. And so you have your X and Y axis, hopefully somewhat straight here. All right. And then we want to go from there. And so they have done this in a, not in a right triangle situation. We'll say it that way. All right. So the first thing we do is we know that it is 0, 5, 0. What is that telling me? Where am I starting? Which direction am I going? Right. So I'm starting true north and I'm going clockwise, right? True north, clockwise. All right. So my first thing is to set up where that airplane is. If he were all by himself in a vacuum, what would it look like? All right. Without the wind being a factor at all. All right. And he's going to be, and again, we're doing this sketching, but that tells us that this right here is 50 degrees. All right. And that tells us that this magnitude here is 310 knots. All right. So far, so good. All right. Now, the other thing we have to look at is the wind. It tells us that we have a 78 knot wind is blowing from a true heading of 125 degrees. Determine the speed and direction of the plane relative to the ground. All right, so true, again, what does that tell us? Right, so a true of 125 means I'm going to start the same direction that I did with the airplane, and I'm going to go 125 degrees. So where is that going to drop me? Fourth quadrant, right? Right, because we're going clockwise, yes. All right, so we're going to go all the way down here. 90 degrees is right at my axis, so another 35 degrees past the 90, right? So another 35 degrees or so past the 90 is my wind. And it's actually going to do something like this, all right? So we're going to have my wind, and it's blowing how fast?
78 knots.
Mm-hmm. All right, and this one, because of how it is doing here, so this is 78 knots. Now, in this case, they slid this guy around, all right? Which you can do. As long as you keep everything the same, you are good to slide this guy around the coordinate plane. It's not going to affect anything. Because what you really want to see is what kind of effect is it having on the plane, all right? Because the wind is not I mean, we drew it down here, but really it's having an effect on the way it's going. And so you want to slide it up here because this is where it's affecting the airplane. If the airplane's going this direction, right, then it's blowing here. It's actually blowing the plane this way, correct? Does everybody see that it's going to blow it that way? Right? It's going to blow it this way. And so it's going to take the plane and it's going to blow it in this direction. And so what they've done is they have taken this little guy and they've just slid him up here. And now I'm going to have to slide everybody down because I went too far up. All right. So they've just slid it up here. So everybody see that? Everybody see why they would have done that?
Yeah, but I see this all the time.
Where's the airplane now? Well, he's going to be somewhere where he started from, which is down at 0, 0. But then he's been shoved this way. Right? So we really want to know what's going on here and what's going on here. Do we not? Like if we want to say his position in the sky at this point, we need to know how far he's actually gone and how many degrees from true north he is, right? Does that make sense? And so we start looking at what we have and what we want. So in this case, we have sides and angles, but we don't have all the sides and all the angles that we need. So we're going to use what we have with what we need. Now, a couple things here. We have to calculate kind of where we are in this process. We do not have all the sides that we need here, and so we kind of have to go based on two sides and an angle, which is why they use law of cosines. So let's review law of cosines really quickly. Really quickly, let's review law of cosines. All right, so law of sines, you may have to use this guy, so let's talk about him. All right, remember we have sine A over side A, right, equals, remember we have this is the easy one, right? So far so good. What's law of cosines? He's a little bit more difficult. A side that we're missing. We have the other two sides that we have or potentially don't have, depending on what we're looking for, right? We have the multiplication of those, 2a and b, and then this is always the cosine of the side that of the angle that corresponds to that side. Okay, right? Does that make sense? And so we are going to use what we have. Well, actually, this is the angle we have, so we're going to have to use it. If we were to take out these two angles, so we have slid this guy up, right? We've slid that guy up. We know what angle he is from the horizontal. And so if we were to take what he is from the horizontal, the 125, and subtract that, we're going to get this guy at 75. We're going to get that guy at 75. So if we subtract those two, we're going to get him at 75. But we can't use law of sines. Why can't we use law of sines? Well, because we don't have the one opposite. So we have to use law of cosines here, okay? We have to use law of cosines here. Now, technically, we're going to end up solving for this little piece right here, because that's the piece that's in my triangle, right? And we're going to have to subtract out to get what's left over. But we're going to use this to solve for that little piece, and we'll subtract it from 50 to figure out what's left over, because we know 50's there, all right? So since the degree that I know is the 75, that's the degree that I know, I'm going to use this as my C, the side across from it. All right.
75.
I took the 125 minus the 50
Okay.
because I just slid that guy up and then subtracted out. So I'm going to say I don't know what C is. That's what we're solving for so that we can actually use law of sines. So I don't know what he is. So we're going to leave him alone. I know my A and I know my B because I know my two sides. I know 310 and I know 78, right? And it actually doesn't matter which is A and which is B. It only matters what's C, all right? So I know my 78 and I know my 310, all right? And then I'm going to, actually this is a minus. I'm gonna subtract my 2 times 78 times 310, and then my cosine of 75 degrees.
I'm confused how you got that angle of 75 at the top.
I subtracted my 125 and my 50. You good?
Why?
Because that's, okay, because you create, this is from geometry, you create parallel lines here, and they're corresponding, they're alternate interior angles.
Okay.
So if I look at this, 125 minus 50 is going to be what's left over here, and I have parallel lines right here. All I did was slide up a parallel line. So it's alternate interior angles, so that means this guy is congruent to that guy. And that guy's 75 because I went 50, 125, what was left over was my 75.
Okay.
And it's alternate interior angles. So that's a review from way back in geometry when you did alternate interior angles. So here's the deal with these. The hardest part of these is visualizing it, okay? Do you agree?
Yes.
The hardest part is visualizing it. That's why it's imperative that you remember what true north and true bearings are, that you recall things like alternate interior angles. So when you create these parallels, you're very often going to use alternate interior. All the time. And just like we did when we did our angle of elevation, angle of depression. That's all you were doing. Alternate interior angles are congruent, okay? It's also very, very important that you are constantly thinking about, am I using the complement? Because when we actually end up solving, we're gonna solve for this angle right here, but we technically want this one. So we have to subtract from 50 at the very end so the reason I drew it on the coordinate plane to begin with, even if you sketch it over to the side to start dealing with the triangle, you have to remember what you're solving for. I am technically solving for this piece of it at the very end. But right here is this piece. So I'm going to have to subtract from 50 when it's all said and done. Okay? So when I calculate all of this, these are all numbers. Two things. One, they're all numbers. Watch your order of operations in your calculator. Make sure you put it in correctly, okay? Make sure when you square something that before you hit the plus sign, you are out of the exponent placing. Some of your calculators pop you into the exponent and keep you there, okay? So if you do 78 squared, get out of the exponent and make sure you do 310 squared. Now, if you have a square button, use that guy because he's going to jump you back out, okay? If you have a calculator, it should do all of this multiplication in one fell swoop. We are in degrees, not radians. Double check your calculator that you are in degrees, not radians, okay? All of these word problems are going to be in degrees, okay? Once you do that, we have solved for c squared. Take the square root of your answer. This is a good time to learn how to use the answer button in your calculator. Once you have done all of this, 78 squared plus 310 squared minus 2 times 78 times 310 cosine of 78, you're going to get this crazy number. You can just hit square root of your answer, which is like your shift in your, if you can find your answer key on here, and it will take the number it just calculated and throw it into the square root for you. You don't have to type in the rounded form of it, okay? Does everybody understand how to use the calculator? 4? All right, so when you plug all that into your calculator, you should get approximately 299.4. It's very important. What did I just solve for? I solved for C, which was part of my answer. Part of my answer was, how far has he traveled? What's the magnitude? So this is technically how far this little guy has traveled, 299.4 knots. That's how far that airplane has gone. So we have solved for one piece of it, right? We now need to know his bearing. We know he started out, I don't remember where he started out, 50 degrees north, or true bearings, 050, right? So we know that's where he started, but the wind has blown him, okay? We know that initially he was going 310 knots, but actually from where he started, he hasn't gone quite that far, right? From where he started. So now we need to know that degrees. So now we have 1, 2, 3 sides of my triangle and 1 angle. So now we don't have to use law of cosines again, nor would I. We can use law of sines, which is a much easier thing to use. So now I can go back and I can say, okay, I don't need him. I have my 75 degrees, so sine of 75 over the guy that's opposite that I just solved for, 299.4 equals, I'm trying to solve for this one, so we're going to use the 78. So sine of the guy that I'm looking for, right, which they use some Greek letter, we'll use just x, over 78. And now I can use cross multiplication, correct? Yes, it's just 2 fractions. Cross multiply. That's all you're going to do, right? So I can say 78.
We're solving for the angle.
The angle, right. 78 times sine of 75 equals 299.4 sine of x, right? Right? Yes, we're just going to use our calculator. I'm not going to make you do that in your head for sure. All right, so the sine then, the sine of the angle that we're looking for equals 79 sine of 75 divided by 299.4. We're going to do tons of these, don't worry. All right? By the way, that's the sine. So in your calculator, what do you need to use? We're trying to find the angle. When you're trying to find the angle, what do you use? The inverse sine. So sine, 78, there we go. Sine inverse of 78 times sine of 75 over 299.4.
Or, wait.
No, not or.
No.
But why can't...
There's no alternate way.
Have that.
Do that, hang on, pay attention. You get 14.6 degrees. Again, what have I solved for? I've solved for this little angle right here, right? This little angle is 14.6 degrees. Am I done? If I ask the question is probably no, okay? Look here. We solved for this little piece right here, but I actually need this little piece. So I need to take 50 and I need to subtract the 14.6, 35.4 degrees. And actually, because it's a true bearing, how do I need to write him? 035 degrees at 299.4 knots is my actual answer and all this craziness. The same exact setup. The airplane's flying. They give us all the information. They give us the wind. So again, I still use a coordinate plane when I do this. So that I can get an idea of where I am in what quadrant I'm in, because it actually makes a difference. All right, and so we have our coordinate plane. And we're going to do exactly what we did yesterday with the drawing to see where everything is. So the first thing we're going to look at is where the airplane is. It says it's 050. So once again, that starts north and that goes which direction? Clockwise, right? So that means this is my vector. My angle here is 50. And the length of this vector is 310. And I'll do these in different colors. So this is 50. That. And this is 310. All right? 310. And you can actually draw this right triangle to the vertical or to the horizontal. I will say that drawing it to the horizontal is going to make more sense to your brain, because then when you start doing opposite and adjacent, it's going to be exactly the same as what you did before. But you can actually draw this either way. By that I mean you could draw it here or you could draw it here. Our goal is to draw a right triangle. Okay? But like I said, when you draw it to the vertical, to your y-axis, then your opposite and adjacent are not x and y like they normally are on the xy, you know, being your sine and cosine. And so always drawing to the horizontal will create that same, your y is your opposite, your x is your adjacent type idea. And so it's not quite as confusing if you do it that way. So I am going to draw this guy to the horizontal. So I'm going to draw it to the x-axis.
I just realized that this is 50 degrees. I thought you said that angle is 500.
That's 50 degrees.
I got that yesterday.
All right, we will make that a little more clear. Make my point a little smaller. And we'll say 50 degrees. Better? And so if we just had the plane to consider, right, then in a perfect world, the plane would go 310 knots, right? But what has happened is we have a wind that is going to blow the plane, all right? And so it tells us about the wind here. It says that a 78 knot wind is blowing from a true heading of 125 degrees. From a true heading. So first we need to find out where that true heading is and realize that it is coming from it towards the plane, okay? And so 125 is going to put us 35 degrees past the 90, right? 35 degrees past the 90. And so it's going to be down here. Oh, we'll do it in this. Here's my wind, all right? 78, he's probably a little shorter than that. All right, 78, and he's going this direction, all right? That direction, because they said from, all right? From. So this gives me a few things to think about. The reason they slid it up here is because really this is what you're going to say is what kind of effect is it going to have? Because it's coming from my, if I'm doing everything on my coordinate plane, then the start of this vertex really needs to be at my origin if I'm going to do this process. And so in order for this guy to be at my origin, I really need him to be somewhere else on the coordinate plane, right? And so when it's like this and I'm actually headed towards my origin, I'm going to just slide it right through. Another way to think about is what effect is it having on the plane itself, okay? On the plane itself, it is pushing, it's going to push it this way, which is going to make my x go smaller, right? Because it's going to push it this direction. And it's actually going to, if I were to take that angle and push it, it's going to make your y go up. Does everybody see that? So if I were to take this guy and push on the tip, I would get closer to my y-axis, so my x would get smaller. And the tip would actually get further away from down here, which means my y would get bigger. So it makes sense that sliding it through is going to do that, because over here, my x is negative. It has a negative effect on my x, and my y is positive. It has a positive effect on my x. Does everybody see that? So if we're doing this process, we really need our vectors to start at our origin. All right? And so I'm actually going to push that guy through. I'm going to push it through. Now, what does that do? Well, this is 35 degrees. Okay? It's 35 degrees. I have created Vertical angles. Vertical angles, it means that if this is 35 degrees, this guy is 35 degrees. Okay? So that means this is 35 degrees. And I am going to do the same thing here that I did over there. I am going to create this right triangle. And I'm going to say the hypotenuse here is 78. The angle measure is 35 degrees. Okay? Now, how does that help me? Well, what I'm going to do is I'm going to take my X and Y movement of the airplane, and I'm going to add to it the X and Y movement of the wind, and I will have a new triangle with a new X and a new Y, okay? And that will tell me, one, what quadrant I'm in. Two, it'll tell me the hypotenuse. I can calculate it, x squared plus y squared, and take the square root. And then I can use SOHCAHTOA to figure out my angle measure. All right, I can figure out my angle measure. So that's what we're going to do. We're going to start with our first one. We're going to start with this triangle right here. And we are going to get our X value and our Y value to get that movement, the movement that that is doing on the airplane. If the airplane went in a triangular motion, how far would it have gone X? How far would it have gone Y? Okay? So how do I do that? Well, if this angle is 50, I really need my angle that's inside my triangle. What is it? 40. Why do you know that? Because it's a 90, and I know 50 of it. So the other part of it must be 40 degrees. So I'm going to use SOHCAHTOA based on that 40-degree angle. All right? And so the sine of the 40-degree angle should equal my Y movement over my 310. And the cosine of the 40-degree angle should equal my X movement over my 310. Everybody agree with that? Based on SOHCAHTOA. Opposite over hypotenuse, adjacent over hypotenuse. And if you always set it up to the origin, it'll be X over hypotenuse, Y over hypotenuse with cosine and sine. Okay? So I'm just going to do it. And so if you calculate that, all right? So I'm going to take, so basically you multiply sine of 40 by 310, right? We're just multiplying across. So Y is going to equal the sine of 40 degrees times 310. Let's not do this in our head. So that's 199. And I'm just going to round to 2 decimal places, 0.26. That is the Y movement of the airplane. All right? Let's look at the X movement. X is going to equal the cosine of 40 times 310. All right? And that X movement there is going to be 237.47. So that's on a perfect world how the plane would move horizontally and vertically. So I'm going to go over here and I'm going to say, well, now I need to figure out what's going on over here. I need to find my X movement here and my Y movement there. All right? Using the 35 degrees. And so over here, the sine of 35 degrees should equal Y over 78. And the cosine of 35 degrees should equal X over 78. Which means that my Y value over here is going to be sine of 35 times 78. And my X movement is going to be cosine of 35 times 78. Yes? All right. So we calculate that. So my sine or my Y value here, is 44.74. And my X value is 63.89. Now, here's the catch. Is my X value positive or negative?
It should be negative.
It should be negative. All right. It's going to always show up positive because I have just created a right triangle doing SOHCAHTOA. This is why it's important to know what quadrant you're in when you do this, because the effect it has on the airplane is in the second quadrant, which is a positive effect on the Y and a negative effect on the X, okay? So when I take these two numbers into consideration to figure out where the airplane is, I need to take that y and add it to that y. But here, I need to negate that movement. So my y value of where the plane is going to be the 199.26 plus the 44.74. I'm going to have a y movement of 244. Okay? The x movement is going to be this 237.47, but I have a negative 63.89 here. So my x movement is going to be the 173.58. Now, both of those are positive, okay? Which means what quadrant am I going to end up in when it's all said and done? When it pushes that plane, where am I going to be? I'm going to be in the first quadrant. So now I'm going to draw down here a little quadrant, my final where am I quadrant, okay? Where am I quadrant? Well, my x value here is 173.58. My y value here is 244. I am trying to figure out my hypotenuse. Okay, I'm trying to figure out my hypotenuse. I'm also trying to figure out this angle. Well, what do I need to do to find that angle? I have a right triangle. I really need to find this angle and subtract from 90. Does everybody see that? Right? Because I really need how far away from north it is. And I'm actually solving it to the horizontal. So when you do this, I am solving to the horizontal. So when it's all said and done, I'm actually going to subtract from 90 to do this. Do you see why that is? Okay. So solving for the hypotenuse, the knots, the magnitude, is just Pythagorean theorem, correct? A squared plus b squared equals c squared. And so to solve for the magnitude, the knots of where this guy is located, I'm going to say a squared plus b squared equals c squared. 0.4. Now, if you check what we did yesterday, you should see that we got 299.4.
Is that 244?
When I have a right triangle, I need to do SOHCAHTOA. I need to do SOHCAHTOA, don't I? So if I want this angle, I can use the sign opposite over hypotenuse if I want to, right? I have all three sides, so I can actually use any one of my three trig functions. But I'm going to say the inverse, because remember, I'm looking for the angle of opposite 244 over hypotenuse 299.4. I get 54.58 degrees. Now, pay attention to what we've solved for. We just solved for that guy right there, right?
Did we not already have that?
So we have just solved for this inside angle, but we actually want its complement. We want this angle right here. How far from north it is. Yes. So we are going to say 90 minus the 54.58. And what do we get when we do that? We get 35.4 degrees. And they just rounded to the whole and they put it in true. So 0.35, which if you will look yesterday, that is what we got. So for this one, it actually is just two axis movements. By that, I mean, there is no angle here. It's due west, due south, it's just like, it's always on the axis. And so it makes it, you actually don't even have to slide your vertex across. You just have to pay attention to what you're doing because you don't have to create a new triangle here. But it says Mitchell swims due east at a speed of 3.5, that would be fast, 3.5 feet per second across the river directly towards the opposite bank. At the same time, the current of the river is carrying him due south at a rate of 2 feet per second. Find his speed and direction relative to the shore. All right. The only thing you do have to think about here is relative to the shore. So we have the shore here, right? And he is swimming due east. So he's actually going just straight from here in this direction. All right, this is 3.5. It says that we have, at the same time, the current of the river is carrying him due south. And so we have this going on here at a rate of 2 feet per second. So this is pretty straightforward. I mean, the hypotenuse here is just created for you, right? I drew it this way because they say relative to the shore, and so we're relative to the y-axis here because that's the shore. You could slide it over and have that 2 at the origin if you wanted to. You just have to keep in mind that you flipped your angle a little bit. So anyway, they want to say how far is he? I mean, how his speed and direction. His speed is going to be my hypotenuse. Like, this doesn't have 2 strange angles. It literally created the right triangle for you. Does everybody see that? It's like if someone was walking one way and turned right or left. Like, it just creates a right triangle for you. And so to do this one, you are going to do Pythagorean theorem. You're going to say a squared plus b squared equals c squared. And so you can, do all of that in your calculator, second square root, use that guy. And you should get 4.03. So 4.03. Now in this particular one, it says from the shore. So once again, I am going to solve for this one. And you are going to have to subtract it back out because they want the distance from the shore, not the horizontal. The shore is actually this thing right here. This is my shore. So I'm still going to use SOHCAHTOA. The sine of that angle should equal my opposite over my hypotenuse. So I get 29.75 degrees, but again, I've solved for this, and they want it from the shore. From the shore. And so they actually want this angle. So once again, I do have to subtract from 90. And you get 60.2, something like that, 60.25. However, when it's from the shore, you're going to have to use like northeast, southwest, etc. Okay? Because it doesn't tell me what you're doing here if you just put 60 degrees. If you just put 60 degrees, I'm going to assume something different. Okay? And so you're going to go back to these directional ones that they gave us. Very rarely are you going to use standard form from something like this. If I have this, though, without anything, they're going to assume standard form. So they're going to assume, if I just leave it like this, that I started here and went this direction, which is not true, right? It didn't push them this way. It pushed them this way. And so I have to say southeast of the shore. So I have to actually say this is southeast of the shore for my direction. And my magnitude is going to be the 4.03 feet per second. All right, two or more vectors with a sum that is a vector R are called components of R. While components can have any directions, often useful to express or resolve a vector in two perpendicular components. The rectangular components of a vector are horizontal and vertical. Here's what they're basically saying. Make a right triangle. There we go. All right. So we are doing it with navigation. In fact, the handout that we're going to do right after this is all navigation, but it also is something you're going to see with work and force. So in a physics setting, you're going to see navigation and you're going to see force as well. And so this is the example that they give us here. Heather is pushing the hand of a lawnmower with a force of 450 newtons. So that is your magnitude, okay? Magnitude. Just like in the navigation when they tell you how fast they're going, all right? That's the magnitude of your vector. So you'll notice they put that 450 newtons right here, all right? It says at an angle of 56 degrees with the ground. So in navigation, you're going to have like true bearing, due west, northwest, or whatever. With the ground is telling you it's from the horizontal. So this would be like a standard bearing in navigation world, okay? With the ground is like a horizontal 56 degrees. And so they have created this guy right here. Draw a diagram that shows the resolution of the force that Heather exerts into its rectangular components. And so you basically just have a right triangle here. We have this right triangle that is created. Oh, that's not what I wanted him to do. Let's see, can we flip him? Nope. All right, and so when you draw it in a rectangle form, you're gonna have, just like they did here, this is your 450. And then this guy right here is 56 degrees. And it says, find the magnitude of the horizontal and the vertical components. So when they say horizontal, they want to know this component here. When they say vertical, they want to know that component there. And because I drew it in a right angle form, I can just use my SOHCAHTOA to do this. And so this is the same concept that we are doing when we do navigation. We are strictly just doing our right triangles and we are seeing how those work together. All right. With the navigation, it's twofold. So we typically have two movements that are affecting it. With this one, it is one. And so we have one movement that is affecting it. Okay. And so we are just going to do our sine and cosine. So if I want to find this guy, I'm going to say, well, the sine of 56 degrees should equal my y over my 450. And my cosine of the 56 degrees should equal my x over my 450. All right. Easy enough. And so when you do that, your x, and they rounded it, your x is approximately 252, and your y is approximately 373. And these are both also in newtons, or whichever unit they gave it to you in. Put it in the wrong. Yeah, I wrote it flipped. So this actually goes here.
Oh, okay.
Yeah, I wrote it and I said it correctly and wrote it under the wrong one. Does that help?
Yes.
I said it right, wrote it backwards. Because you know. What is that whining?
That's the computer, the fan.
What computer's fan? Why is your computer open? There we go. We don't need a computer open. And it's still whining. There we go. All right, so try one. I know. I'm like. I debated back and forth between 8-2. Because 8-2 just does like number crunching of what we're doing, but we'll do it. It won't hurt us to do it again. Number crunching form. They actually kind of already have it for you. You just have to drop that straight line down to make it a right triangle. Yep.
This is
The magnitude is the length. They're basically just saying the length of the base and the length of the height. When they say magnitude, in a right triangle world, it's a length of something. They've given you the magnitude of the hypotenuse, basically, and they want the vertical and horizontal. So it's just SOHCAHTOA.
So we're literally just solving for X and Y every time?
Yep. We're about to do the same thing in navigation. Yes. All right. So for this guy, it basically drew it. I mean, if you wanted to complete this, we're talking it should have looked like that. Your right triangle should look like this, right? And when you find your horizontal and vertical, you should have gotten 36.9 and 23.96. X was your horizontal, Y was your vertical. Yes? Question? This is your X. This is your Y. So you would have said sine of 33 equals Y over 44. Cosine of 33 equals X over 44. In your calculator, you would just multiply